Welcome to our video lecture series of fax devices. We are continuing to discuss about the voltage and the phase angle regulator devices. We have seen how it will control and principle of operation in previous class. Now, we shall see that hardware implementation of this voltage and the phase angle regulator. Now, we shall discuss mostly the two type of devices. One is voltage and the phase angle regulator. In this category, we shall discuss about thyristor control voltage regulator. This is basically it injects voltage in series or quadrature as it has been discussed in previous class, and thyristor control phase angle regulator. It controls the phase. And another is actually the switching converter based voltage and current phase angle based regulator. First one is thyristor based, it is primitive, and second one is basically GT or the IGBT based. Now, we shall discuss about historically these two came fast. So, first we will discuss about the TCVR and TCPAR. So, these are both thyristor control, thus you have a control on the turn on and it has to be commutated or it has to be line commutated by turn off. So, for this reason thyristor controller, the voltage and the angular regulator provides a voltage with a variable magnitude from the fixed voltage source by changing the firing angle of the thyristor. This thyristor control does not intentionally change the angle of the voltage. So, that is something we require to understand it. That means, voltage regulation based on the delay angle control does result in shape angular shift. You know that actually there is a different kind of quantity when we have studied power electronics. So, we got displacement power factor. So, when you delay by some angle alpha, so then there will be a delay in power angle also. Thus, whether the regulator arrangement is a voltage or an angle is determined entirely by the transformer winding configuration. We require a different kind of transformer winding, and from there we inject phases in different way, that we will see and discuss in our subsequent topics. So, the following discussions voltage and angle regulator will not be distinguished. The reference will be only actually categorized as the regulator. So, it can be voltage regulator or current regulator. So, it is just a controller, topology wise you do not find any change in it. Thyristor controller used in voltage and the angle regulator will be referred as thyristor tap changer or thyristor based tap changer. These thyristor tap changers may be configured to provide continuous or discrete level of control. So, you may have a step change or you have a continuous change, we have a number of switches that will increase. The continuous control is based on the delay angle control, similar to that of the introduced into the induction regulator, and thereafter it have a drawback of the delay angle control, and definitely the most basic problem is that it generates the low frequency harmonics. And to reduce the harmonic generation, thyristor step changer configuration must be provided with a discrete level of control, that you will see subsequent topic that how it can be done. There is a number of possible configuration capable of the discrete control with tap size comparable those generated by conventional electromechanical unit. We know that there is a tap changing transformer when it is a very common practice in our distribution transformer in the peak hours when actually demand goes high, then output voltage of the transformer goes low. So, we require to actually put it to the higher taps. Some of this arrangement can be lead to the reduction of the number of transformer taps required. Two basic thyristor tap changer configurations are identical winding and thyristor valve rating and its winding of the thyristor valve rating and the tertiary progression. These are few configuration we shall cover in our topic. So, this is the one of the configuration of the tap changer. First method is for the regulator. We shall cascade n such regulator, n identical winding and the bidirectional thyristor bridge circuit provided from 0 to n voltage steps in either direction. So, in that way you actually increase the level. So, you can bypass also. So, you can take this way. So, then this network, this actually magnetic path is bypassed. So, number of turn is reduced and you can increase or decrease the number of turns depending on the switching of the thyristor. In that way you control it, and since there is no delay angle control, ultimately you will get less harmonic. Since each bridge circuit can connect the related to the transformer winding with their polarity or can bypass it. So, this is the case. Second one is based on the tertiary progression. We can have any mathematical progression, that is that may be 1:3:9 or 1:2:4, something like that. The transformer winding and the voltage rating of the thyristor bridge are proportional with the ratio of 1:3:9 and the number of steps n in the directions given with the number of the winding, and by the expression is 3 to the power L minus 1 by 12. So, this will have a 9 turn, this will have a 3 turns, this will have a 1 turn. In that way actually it has been configured. So, if you like to actually increase a little bit voltage, then you can actually use in it, or you want to actually reduce the voltage injection phase, then you may bypass this magnetic path. And another is a continuous voltage regulator. It is also a simpler circuit. The continuous voltage control is implemented by using phase delay angle control. This is a basic approach. For let us say some angle alpha, they actually this thyristor is switched on, and maybe after some angle this thyristor is switched on, or vice versa. Then actually voltage profile will change, will come across the voltage profile in subsequent slides. The two thyristor valve employed need only by the rated according to the maximum percent of the voltage is required. This schemes giving continuous control suffer from, but it at a few drawbacks. These suffer from these two drawbacks. They definitely will create harmonic. They create harmonics of the supply frequency in their terminal voltage, and implementation of the control for all load and the power factor is relatively complex, because you know that there is a lagging power factor, then current and voltage will be in quadrature, then it may not be automatically commutated also. So, what should be take away from these discussions? The output of a continuous control regulator in a single phase, odd harmonics of the systems will actually present, because we have a odd symmetry we assume. So, odd harmonic will be present. In case of the 3 phase with identical load control setting, all the 3 phase will and if you employ a 6 pulse converter, then usual 6 pulse type harmonics in order of 6 m plus minus 1 will be actually present and will be contaminated with 5, 7, 11, 13 with these harmonics, where m is the integer ranging from 0 to infinity. The number of thyristors required for voltage regulator application is heavily influenced by the actual transient voltage current occurring during the surge and the fault. So, we have to take care of these issues. So, surge and fault is something we have to see. So, according to the we choose the voltage rating and the size of the thyristors and the number of thyristors. So, there is a number of possible thyristors chap changer configuration, it is one of it, which can give continuous control with varying degree, but its circuit is quite complex. The basic power circuit schemes of the thyristor chap changer is considered here. This is actually the circuit. So, ultimately V1 will be applied when SW1 is closed. So, profile will be something like this. Thereafter, after a delay of some angle alpha, then this switch will be closed automatically, So, the conducting thyristor will be reverse biased and there will be a surge in voltage. Again here actually you may close this thyristor. So, this kind of waveform you may generate. We are coming to this waveform in subsequent slides. The basic power circuit scheme of the thyristors of a tap changer is considered. This arrangement can be continuous voltage magnitude control by initiating the onset of the thyristor pulse conduction. We can start from at the alpha equal to 0. Assume that a resistive load is connected to the output terminal of the tap changer, we shall see the waveform. So, this is actually V1 lower thyristor where it is connected, and this is a V2 where upper thyristor is connected, and this will be the new profile of the voltage. So, therefore, for the line current in phase with the terminal voltage of the resistive load is been shown here. The two voltage obtainable at the upper and the lower taps are V2 and V1 respectively. This is V2 and this is V1, this is V2 peak and this is V1 peak. The gating of the thyristor valve is controlled by the delay angle alpha with respect to the voltage 0 crossing of these voltages. At alpha equal to 0, in the present case a resistive load, the current crosses 0 and thus previously conducting valve turns off. Valve SW1 turns on to switch the load to the lower tap, and thus we obtain this profile like this. This is for alpha and this much to this much is actually pi plus alpha and this kind of voltage profile. In assignment we shall provide, we shall ask for this actually harmonic content of this waveform and we require to calculate the fundamental value of it. So, that will be given to the assignment. Students are expected to actually find it out the harmonic contents and the fundamental of this kind of type changes. At alpha equal to alpha 1, so the valve SW is switched or gated, on which it commutes current for the conducting thyristors of valve SW1 by forcing the a negative anode to cathode voltage across it, because when this thyristor is triggered, assume that it is a positive half cycle, the negative voltage is applied across this conducting thyristors and automatically this will be turned off. Then the connecting the output of the upper tap with the valve and having a voltage of V2. The valve V2 continues to conduct until the next current reaches to 0 in the present case, and if it is a load is inductive, then it will conduct till the current through the thyristors actually goes below the holding current, and the next current 0 coincides with the 0 crossing for alpha equal to 0 because it is a resistive load. This waveform indicates that by delaying the turn off of SW2 from 0 to pi, any output voltage between V1 to V2 is attainable, and ultimately you require to calculate the fundamentals of this step changed waveform. So, let us see that how it can be calculated. So, Fourier analysis of the output voltage of the waveform for an idealized continuous control thyristor tap changer is shown below, yielding to the following expression for the fundamental component. So, let us assume that V1 is represented by A1 and V2 is represented by B1. These are the fundamental value of the voltages of these two voltages. So, this V off will be actually A square plus B square. So, ultimately tan theta, that phase difference will be now tan inverse A by B, where V off is the fundamental of the phi off, and there will be a phase delay of the fundamental. So, with respect to fundamental, the unregulated voltage A1 will be V2 minus V1 by 2 pi cos 2 alpha minus 1, and similarly we can calculate B1 by Fourier series analysis, that will be V1 plus V2 minus V1 by pi minus alpha plus sin 2 alpha by 2. Again, these equations will have a problem, we have to solve in an iterative method by different value of alpha. So, let us see that how phase angle and the output voltage changes with different alpha. The variation of the amplitude of VOF and the angle, phase angle phi f0 of the fundamental voltage with delay angle alpha for an assumed 10% regulation range has been shown. The fundamental component of the regulated output load voltage generally lacks the unregulated supply voltage range of 0 to pi. So, alpha can be varied to actually 0 to pi even with the unity power factor. So, power factor can be actually manipulated here, even in resistive power factor you can get a inductive kind of loading by the tap changer. So, this is the VOF. So, when it is actually at 1 alpha equal to 0, so you get 10% more voltage, as simple as that, and gradually it will come down and you get actually 10% less voltage, and this is the reference, and you get 0.9. And what about the phases? So, maximum lagging phase will occur in and around 90 degree, So, this will be the phase change due to the 10% trapping, that if tapping changes then phase angle also changes. So, what about the harmonics? The harmonics of the output voltage we can actually represent in the following way. So, this is actually AN. So, AN will be actually V2 minus V1 by pi 1 by n minus 1 minus 1 by n plus 1 plus cos n plus 1 alpha n plus 1 and n minus 1. Of course, actually you can eliminate a particular harmonics here, let us say by choosing a particular value of alpha. So, that is comes under the section of the selecting harmonic elimination, but then these are actually stepping may be actually loosed. So, similarly Bn we will have V2 minus V1 by pi sin n plus 1 alpha n plus 1 minus sin n minus 1 alpha by n1, and where actually n equal to k plus 1 and k's are 1, 2, 3, 4. The dominant harmonic component as a percentage of the nominal fundamental voltage will be actually V 1 plus V 2 by 2, the average value. The amplitude, that is what it is. So, it will be actually V 1 plus V 2 by 2, and this is a percentage of it. And you see that how it is changes with the delay angle, and this is actually third harmonic, and third harmonic will have a huge, actually we will have a content around 4 times of the, actually it is in percentage. So, there is a high percentage of third harmonic will be present, it is around 4%. So, we have to suppress that harmonic to have a prescribed norms of THD of less than 5% for practical operation. Same way we have a fifth harmonic peak, and same way we have a 7th harmonic peak. At 90, generally 5th and 7th content of the 5th and 7th are same. So, the THD actually will be quite high. The amplitude of the harmonics at any given angle alpha are of course proportional to the regulation range. The output voltage shows the maximum third harmonic distortion occurs at a delay angle equal to 90 degree, and the maximum strength of the fifth harmonic will have a delay angle of 120 degree. So, we have to see that how you can reduce those harmonic content. Now, what happen if instead of this actually the resistive load, most of the load are inductive, you put a heavy inductor. This thyristor step changer with highly inductive load. So, what happens, there will be a lagging current, this I, and this is V 1 and this is the V 2. In this case, the unidirectional thyristor valve capable of conducting only positive or only negative current are labeled individually, because the current has to be in this cycle. A positive valve at a lower tap labeled as A, and the negative are labeled as B. Similarly, let us consider that upper tap, this is A, this is B, this is C, and this is D. Similarly, the upper tap of the positive valve is labeled as C, and the negative tap is labeled as D. The voltages at the upper and the lower tap together with an inductive load current of arbitrary magnitude is chosen as a reference. Let us see that what happened then. Then we require to manipulate in different way. So, we will be actually in case of the PWM technique, we try to discuss about few PWM technique. The typical case of the actually 60 degree bus coupling method. Thus, these are the voltages V 1, V 2, and this is the I, it is phase lag by 90 degree. Thus, what happened, the changing the first from the upper to the lower tap. So, operation will be different. First the upper tap will be switched on, followed by the lower tap, and then from the lower to the upper tap to be carried out during the positive half cycle of the supply voltage. At alpha equal to 0, the inductive load current is negative. So, for this reason, what happened, for the interval of voltage V equal to voltage at 0 current, which is almost at pi by 2, because of it is assumed to be very highly inductive or almost 0 resistance. The commutation of the lower tap is possible by turning of the thyristor valve B of the lower tap. This action will impose a negative anode to cathode voltage on D and forcing them to turn off. So, this is the way you can turn off this actually forward going thyristors. Then what happened? because previously the negative cycle was conducting. In this subsequent interval, the positive voltage half cycle and the current 0 crossing to the next voltage 0 crossing, the current is positive. So, either thyristors A or C will be basically flowing or gated. So, we can get either of the thyristor, and if you try to reduce it, we get basically thyristors A. But commutation would be possible only from the valve A to C, not C to A, please mind that. So, turning on the valve C impose a negative anode to the cathode voltage A to turn it off, and but C could stay in conduction until the natural current or the holding current of the thyristors current crossing 0 reaches, because C is connected to the higher voltage tap in some way for the negative half cycle of the power supply. And thus what happened? From these results, it can be seen that the positive time progression from the voltage 0 to current 0 in any half cycle, when thyristor tap changer is supplying the resistive load, only one tap change from lower to the upper tap can take place. That is what we have seen, and this is because the voltage and the current zeros and it coincides with each other and for the tap change D to B or C to A controlled by the delay angle alpha can occur any angle or voltage 0 to the 0 current, to the current 0. That means the interval can be 0 less than alpha 1 to phi, where phi is the basically delay angle, phi is actually the phase angle of the current. The tap change of A to C or D to B controlled by the delay angle alpha 2 can occur any angle current 0 or the voltage 0, that means with the interval phi actually less than alpha 2 and till pi. This is the mode of conduction for inductive load. Now, we shall continue with the capacitive kind of loading in our subsequent classes, and we shall see here there will be a little change here definitely, as you understand that current will lead basically the voltage, supply voltage. So, turning pattern will definitely be expected to change. Thank you for your attention. We shall continue to our next class with these discussions.